Okay, good afternoon, everyone, and welcome to Carl Monismith Lecture. But before we introduce our distinguished speaker, I would like to take a moment and talk about Carl Monismith. Professor Carl Monismith was a giant in pavement engineering, but what truly set him apart was his humanity. His pioneering work in cracking and fatigue, shear testing, and finite element method transformed our field. Yet he remained humble, warm, genuinely invested in the people around him. Carl never stopped pushing boundaries. He was among the first to apply servo-hydraulic systems to asphalt testing. His belief in shear as the leading cause of asphalt concrete pavement, once rejected, is now proving more relevant than ever. He did not just ask the right questions, he built the tools to answer them. I experienced his generosity from the very beginning, shortly after I got my PhD. He reached out personally to connect me with one of his newly graduate students. Once I fell ill during his visit with me at Virginia Tech, he called several times afterwards just to check on me. That was Carl. Technically brilliant, but above all, a deeply compassionate man. When I moved to the University of Illinois, he was the first person I invited to lecture. Even in his final days, he continued to show up. He moderated a session at AAPT, taking calls and staying engaged with the work he loved. He was a builder of knowledge, cultivator of people, and a model of what it means to lead with purpose and grace. In his honor, the University of California at Berkeley has established a scholarship in his name, a fitting tribute to a man who devoted his life to shaping the next generation. Those who wish to carry his legacy forward are encouraged to be part of that. We were fortunate to know him, and his legacy will live on in every engineer who stands on the shoulder of what he had built. So with that, it's my true pleasure to announce that our recipient for this year is Nav. So Nav, please join me on this. I'm gonna let you sit down again. This is the Carl, I'm gonna say here. This is the Carl Monismith Lecture Award, and it's in recognition of demonstrated leadership, achievement, and contributions to the advancements of pavement engineering. And it's my opinion that Nav is one of the best people who can receive this award, because Carl Monismith, he worked on the subgrade all the way to the asphalt. So, Nav, it's a pleasure.
Thank you very much.
Okay. Now I think it's my pleasure to introduce Nav. Dr. Nav Garg is a program manager in the Airport Technology Research and Development branch at the FAA William Hughes Technical Center in Atlantic City in New Jersey. He holds a PhD from the university, which is University of Illinois at Urbana-Champaign in 1997, and degrees from Illinois Institute of Technology and the National Institute of Technology in India, all in civil engineering. Since 1998, Dr. Garg has led airport pavement research at FAA, managing projects on accelerated pavement testing, resilience, and pavement materials, and led many national projects. He conceptualized the FAA National Airport Pavement and Materials Research Center, which is a $9 million state-of-the-art facility and has authored more than 125 peer-reviewed papers. Dr. Garg is a fellow of the ASCE. He's the vice chair of the ISAB and associate editor of the International Journal of Pavement Engineering. He's the recipient of several honors, including the 2023 UIUC CEE Distinguished Alumnus Award, and the FAA Ellis Ousted Award for Technical Excellence. He's also the 2023 University of Illinois Urbana-Champaign Chi Epsilon, which is the National Honor Society of Civil Engineers Profession, a chapter honor member. So I can't keep going and going, but we definitely wanted to listen to Nav today. He's a great family member, and he has 2 kids, and his daughter is more brilliant than him. I'm putting this on record. Since she was a kid, that's always what I say. So Nav, we're very honored to have you received the Carl Monismith Award, and we look forward to your lecture. Please join me in welcoming Nav.
Thank you very much. Thank you, Professor Al-Qari. I'm truly humbled and honored to receive the 2026 Carl Monismith Lecture Award. I would like to thank my nominator and the individuals who supported my nomination, and to the ASCE Geo-Institute Board of Governors for approving it. Now, I never had an opportunity to interact with Professor Carl Monismith, but for a brief interaction at TRB when I was a PhD student. My PhD advisor, Professor Marshall Thompson, introduced me to him. But everyone knows, like whoever is in pavement field, they have been influenced by Professor Monismith's teaching or research in some way, and I'm no exception. So with that, I'll go into my presentation. And actually before that, I would like to acknowledge the recipient of previous Carl Monismith Award. And I've had the privilege of working with a lot of people who are listed in this list. So my topic today is advanced material modeling for airport pavement design for next generation aircraft. In 1998, I joined Galaxy Scientific Corporation, that was a support contractor to Federal Aviation Administration, and they were building a national airport pavement test facility at that time. So my previous work was in low volume roads, so moving into airport pavements was something very exciting for me. And this just shows the layout of the facility. There were 3 different subgrade types: low strength, medium strength, and high strength. And there were 3 test sections built on each of these subgrade types: 1 concrete and 2 asphalt pavements, 1 with a stabilized base and 1 with a conventional aggregate base. And this slide shows some of the cross sections. Now you will see that the pavement cross section, the thicknesses are different. And the reason for that is all the asphalt pavements and the concrete pavements, they were designed to fail in 10,000 passes of a Boeing 747 gear at a wheel load of 45,000 pounds. So the loading condition was same for all, the subgrade conditions were different, and that resulted in different pavement thicknesses. Traffic testing started on 14th of February in 2000, happened to be the Valentine's Day, and north side was tested with 6-wheel gear, and the south side was tested with 4-wheel gear, and this figure here shows the wheel spacing and the axle spacing for the loading gears. The test speed was 5 miles per hour because for airport pavements, the most damaging condition is when the aircraft moves from gate towards the runway. So testing at slower speeds is more desired. The failure criteria for flexible pavements was 1 inch of upheaval outside the traffic area, signifying shear failure in the lower layers of the pavement structure, especially subgrade. So we started testing, and then what happens is these pavements were designed for 10,000 passes. Concrete pavements had corner cracks in 28 passes. That was shocking. We stopped testing, and we had to do a lot of work on concrete pavements to figure out why that happened. And once we determined that, then we continued testing on our asphalt pavements. Now, again, they were all designed to fail in same number of passes, but medium strength subgrade sections failed much earlier than the low strength sections. That was very shocking for us too. And in the high-strength subgrade sections, we tested till 5,000 passes and we did not see any significant amount of distress, which was rutting. So we stopped testing on those sections. After 20,000 passes at 45,000 pound wheel load on the low-strength sections, we increased the wheel load to 65,000 pounds. That's a significant increase in the wheel load. And we put additional 30,000 passes, and still those sections did not show any signs of subgrade failure. So that, on this figure, you can see the rutting results. These are the low-strength sections that failed right around 10,000 passes. This is the medium-strength section with stabilized base, and these are the low-strength subgrade. Right here is where we increase the wheel load to 65,000 pounds. So that brings up a question like, what is there in our design procedure that we are not able to predict pavement life? We know predicting pavement life is difficult, but still, that's a huge difference. So that prompted me to go into the history of airport pavement design, what's there, how it evolved over time to reach where we currently are. So in the next segment of my presentation, I'll talk about the history of airport pavement design. Work on airport pavement started in 1940s because of World War II. So the work was being done by US Army Corps of Engineers. And in 1940s, they built some test sections. And before that, the performance curves that were available were for highway pavements. So they had design curves for up to 7,000 pounds as a function of CBR of the subgrade. So US Army Corps of Engineers extrapolated these curves to 40,000 pound wheel loads. But then there were these new bombers coming up, B-36 and B-29, that had wheel loads of around 100 to 200,000 pounds. That's a pretty significant heavy aircraft. And you can see the size of the tires in this figure. So they built these test sections to extrapolate those design curves to 100 to 200,000 pounds. And it's very important to note that the person who wrote the report for Stockton tests, Mr. O.J. Porter, he made it a point in his report, if you read, he said, CBR is a good method now, but we should try to move away from that into other test procedures that quantify the bearing capacity of the soil and the strength of the soil. And stress ratio is something that we should be looking at. But over the years, US Army Corps of Engineers has done testing at different Air Force bases, but most of the testing has been done at Waterways Experiment Station in Vicksburg, Mississippi. And different load cards were developed over time to test for different aircraft, and you can see some of those load cards in this slide. So from 1940s to 1970s, all the testing was done by US Army Corps of Engineers, both over asphalt pavements, concrete pavements, and on overlays. And the performance data that was generated from these full-scale tests formed the basis of airport pavement design procedures for both the Federal Aviation Agency, as it was known at that time, and the Tri-Services Manual. And one of the major test series that was carried out was also known as multiple wheel heavy gear load study. And it was the arrival of Boeing 747 aircraft that had four-wheel gears that necessitated the need for multiple wheel heavy gear load study. So all the information that came out from these studies were implemented in the form of nomographs. And the first FAA advisory circular that dealt with pavement thickness was Advisory Circular 5320-8 that was issued in 1963. And as you can see in this nomograph, you have single wheel load on the y-axis, and you have pavement thickness, total pavement thickness on the x-axis, and then you have the gross weight of the aircraft as a with the gear type. So for this chart is for dual tandem, and they had soil types for different subgrades. There is no CBR. There is no consideration for number of aircraft operations or departures. And asphalt thickness was specified as 3 inches for critical areas and 2 inches for non-critical areas. And as more data was being accumulated, the charts were being modified, charts were being added for new aircraft as they were coming out. And this particular advisory circular was issued in May 9th, 1967. And again, you have these nomographs for different landing gears, different aircrafts, but still there is no consideration of the aircraft operations. In 1995 was issued Advisory Circular 5320-6D. This particular advisory circular, the nomographs included CBR of the subgrade, aircraft operations, and the design procedure required you to convert departures of each aircraft into design aircraft, departures of design aircraft. And once you have the departures and your design aircraft determined, you would go to the nomograph for that particular aircraft and come up with pavement thickness. Now, as the airport pavement design procedures or nomographs were evolving, so was the commercial aircraft industry. What you see here is the aircraft used for one of the first commercial aircraft service, and you can see very small wheels, wheel loads of less than 15,000 pounds. Then came Boeing 747, wheel loads jumping up to almost 44,000 pounds per wheel. And then in early 90s, there were two aircraft on the design boards, Boeing 777 and Airbus. At that time, it was called A3XXX, that later on became A380. And now you're looking at wheel loads of over 60,000 pounds. And the ICAO methodology that was used at that time by different member states to look at aircraft airport compatibility was called ACN PCN, or Aircraft Classification Number and Pavement Classification Number. And the way ACN PCN methodology works is, if your ACN is less than or equal to PCN, you can have unlimited operations of that aircraft on that pavement. ACNs is the responsibility of aircraft manufacturer. PCNs have to be computed by the airport owners. Now, when you start evaluating pavement thicknesses for the new aircraft, most of the airports in the world would require to increase the thickness of their pavements or strengthen their pavement structure. Now, if you can't land an aircraft on a runway, it's very difficult to sell those aircraft. So Boeing did some tests in Russia and found that ACN PCN methodology is highly empirical, that does not consider the effect of multiple wheels on the gear and has a lot of conservatism built into it. So Boeing worked with FAA and went to US Congress, and we got about $14 million to build National Airport Pavement Test Facility in Atlantic City, New Jersey, to look at the performance of pavements under 6-wheel gear and compare it with a 4-wheel. And actually here, currently, if you look, we are in this next generation of aircraft where Boeing has Dreamliner 787 and Airbus A350 that has some of the highest wheel loads. And what you see on the chart on the top, as you go from left to right, is the increase in wheel loads over time. So currently, the maximum wheel load is around 73,000 pounds for A350-900. And the green line is the capacity that we have at our test facility to test if aircraft industry comes up with an aircraft with a higher wheel load. Now, as the wheel loads go up, these tires work on rated deflection, so the tire pressure goes up. And the chart at the bottom shows how tire pressures have increased over time. So in the current commercial aircraft fleet, you're looking at tire pressures of around 250 PSI, which is a significant increase compared to Boeing 747 that was around 220 PSI. So while there was testing going on, the researchers at FAA thought that with the 6-wheel landing gear, it is very important to consider wheel load interaction that takes place at lower depths in the pavement structure in the base, subbase, and subgrade level. That's something that cannot be done using CBR equation that was the basis of previous design procedures. So that led to the development of LED FAA, which stands for Layered Elastic Design for Federal Aviation Administration. And They looked at pavement thickness designs using LED FAA for the existing aircraft, and they were compatible with what thicknesses you would get from the nomographs. So FAA made a policy that if any aircraft traffic mix has a six-wheel landing gear aircraft, which was Boeing 777 at that time, the designers were supposed to use LED FAA for pavement thickness design. If your aircraft traffic mix did not have 777, then you could use the old nomographs. When we started using LED FAA and were refining our failure models based on the full-scale test data that we were generating at NAPTF, we found that LED FAA should be fine for any kind of traffic mix. So in 2004, FAA issued Change 3 that canceled Advisory Circular 5320-16. This was the advisory circular that required use of LED FAA. And LED FAA was made an alternate procedure for all thickness designs, whether your aircraft traffic mix has Boeing 777 or not. So this was the first attempt at a mechanistic empirical pavement design procedure. So let me go over this flow chart. These are the parts of mechanistic empirical design procedure. The first step is your inputs. You characterize your materials. What materials are you using for construction of your airport pavement? Climate, how is it going to affect your pavement performance? And traffic. Remember in the previous design procedures, we were looking at a design aircraft. That was the traffic model for those design procedures, but we had new ideas for mechanistic empirical design procedure. So all these inputs are then fed into a structural model. So in LED FAA, it was a layered elastic analysis. And the structural model would predict critical pavement responses such as stresses, strains, and deflections, which are then related to pavement performance through the use of transfer functions. And this part here, the transfer functions, is the empirical part because this is based on the observation under full-scale tests or at actual airports. And that's probably one of the reasons why maybe it'll be very difficult to have an entirely mechanistic design procedure. So while LED FAA was being used, we were also working on developing a finite element-based design procedure, and that was FAR-Field. FAR-Field 1.3 was released in 2009, and the advisory circular that was issued by FAA at that time was 5320-6E that required you to use FAR-Field. It replaced all the nomographs and LED FAA. Now, if you look at the user interface, if a person had used LED FAA, using FAR-Field was exactly the same because all the improvements and advancements were in the background. And FAR-Field had layered elastic analysis for flexible pavement design and used 3D finite element for concrete pavement design. And this chart here shows the differences between the nomographs and the FAR-Field. So when you look at the traffic model, we used a concept of design aircraft in the nomographs, whereas in FAR-Field, we used the concept of cumulative damage factor, or CDF, where we are looking at damage caused by each aircraft in the traffic mix, and we add that damage. When you look at the structural response models, for rigid pavements, we were using Westergaard solution for the nomographs. For flexible pavements, we used equivalent single wheel load that was computed using Business model, whereas in FAR-Field, we used layered elastic analysis for flexible pavements and 3D finite element for rigid. Thickness design method for flexible pavements, it was CBR equation in the nomographs, and in FAR-Field, we used failure models that were developed based on full-scale test data, and we looked at the entire history of full-scale testing from 1940s till mid-2000 to develop those failure models. And implementation of old 6D was in the form of nomographs, whereas with FAR-Field, it's form of a computer program. The latest version of FARfield that you can use currently is FARfield 2.0. And here is a screenshot of FARfield 2.0. It has a much more modern look to it. The failure models are still same compared to FARfield. For flexible pavement design, the two predictors of pavement life are the horizontal strain at the bottom of asphalt layer that relates to fatigue failure in the asphalt material, and maximum vertical strain on top of the subgrade that relates to rutting in the subgrade, which ultimately causes shear failure. So how do we account for traffic in the new design procedure FARfield, or what we currently have, the state of the art? So what this figure shows is, this is the runway center line, and these are the locations of landing gears for different aircraft. Because unlike highway pavement where traffic is highly channelized, traffic is very distributed for airport pavements. So we'll look at the cumulative damage factor, which is the summation of damage caused by individual aircraft, and then sum it up. When your CDF value reaches 1, that means you have utilized the entire life of that pavement structure. So in FARfield, the gear location and wander are considered separately for each aircraft in the traffic mix. You know, pilot tries to put nose wheel gear on the center line of the runway, but you still see some wander. And that wander depends on what type of aircraft you're in. So that's considered. And the CDF is calculated for each 1-inch or 10-inch wide strip over a total 20.8 meter width. That's where we compute for each 10-inch strip. And we look where is the critical location, and the CDF coming from each aircraft at that location is summed up to design your pavement. And we use Miner's hypothesis to sum up the damage. And this figure explains that part. So we are showing two different aircraft, airplane A, airplane B. The difference between their peak responses is because of difference in the gear location. And when you sum up the damage from each aircraft at each location, what you get is the red curve, which is the total damage caused by these two aircraft. And that is what is used in the thickness design. For climate, a design procedure does not consider climate explicitly, but what we do is we have Advisory Circular 5370-10H that provides material specifications and construction specifications, and that specification gives you guidance on how to select different binder grades depending on which temperature region you are in the country. So next, I'm going to talk about material characterization, how it is done today. So this chart summarizes the material properties that are used in airport pavement design procedure FARfield. You know, in layered elastic of finite element, the material property that is input is the elastic modulus of the material. And this table lists the moduli values that are used for different materials. And to summarize the table, what you find is that the modulus of asphalt concrete is fixed at 200,000 psi. So it does not matter what binder grade you're using, what temperature it is, the modulus is fixed. For aggregate and subbase, the modulus is computed by a routine that is embedded in FARfield, and it looks at internal sublayering and then assigns modulus values, with modulus value increasing from bottom to top, and that sort of accounts for the confinement, because your confinement will reduce as you go down in the pavement structure. For subgrade soils, the users can input elastic modulus, but most of the time CBR is the value that is available, and CBR is converted into modulus by multiplying it by 1500. And that's also raises some issues, because if you look at the relationship between modulus and CBR in literature, there is a wide variation in those modulus values. So which relationship do you really use? The one that FAA uses comes from the Shell design procedure, 1500 times CBR. Structural model, we already talked, it's layered elastic analysis for flexible and 3D finite element for rigid. And the pavement responses, we are looking at strains in the asphalt concrete and vertical strains on top of the subgrade. So the failure model that is embedded in far field is based on the ratio of dissipated energy change. And this work was done at University of Illinois by Professor Sam Carpenter and his PhD students. And there is a report and paper listed at the bottom if you want to get into more details. But the number of cycles to failure in fatigue is a function of plateau value, and the plateau value is a function of strain in the asphalt, the flexural stiffness, the void parameter, and gradation parameter. Now, this flexural stiffness, so this model was developed based on 4-point bending beam fatigue tests. So what this design procedure does is measures the flexural stiffness of the beam for first 100 repetitions, and failure is considered when the stiffness reaches 50% of the initial value, which signifies formation of microcracks in that asphalt beam. And the void parameter and gradation parameter, they are coming from your mix components. So if you know what asphalt mix you have, you can compute your gradation parameter and the void parameter and compute your number of cycles to failure. Now, we did do some tests in construction cycle 7 so to validate and refine the model, and we found was that the number of cycles that it takes to cause alligator cracking, because in field, fatigue is defined by the occurrence of alligator cracking, and we found that it takes about 3 times the number of cycles predicted by this model to get to the alligator cracking, and which makes sense because the failure in the model is reduction in stiffness to 50%, which is microcracks, whereas alligator cracking, you're looking at almost full depth cracks in the asphalt layer. For subgrade, it's a kind of bilinear model. We have one equation when the coverages are less than 1,000, and another equation when coverages are less than or equal to 1,000. So that's the current state of the art of our pavement design procedure, the responses that we use for predicting pavement life, and the material input properties. But what was the reason why there was such a big difference in pavement life that was observed, even though the sections were designed to fail in 10,000 passes? So the next section of the presentation, I'm going to talk about what we observed in the full-scale tests from 2000 till now, and that may help explain why there is such a big difference by the predicted life and the actual life. So we'll start from the top layer of the pavement, the asphalt material, the asphalt layer. So if you remember, in design, asphalt modulus is fixed with no consideration given to the binder grade or the temperature effects. So this was some research that was done at National Airport Pavement and Materials Research Center, where we have the ability to control pavement temperature and test these sections under controlled temperatures. So as you can see on the left side, we have 2 lines for each material. There is one is warm mix asphalt, the other is hot mix asphalt, and this is for PG 64 minus 22, so unmodified binder, but tested at 120 degrees and 90 degrees. These temperatures are 2 inches below the pavement surface, so when I say 120 degree pavement temperature, you're looking at surface temperatures of around 160 to 170 degree Fahrenheit. And you can clearly see the difference in the performance. These sections, here the failure criteria was 1 inch of surface rut. You have pavement sections failing in less than 200 passes, whereas at 90 degrees, you're close to 3,000 passes. So that's a pretty significant effect of temperature. Same thing for polymer modified binder. The right curve is for polymer modified binder PG 76 minus 22. And of course, it gives better performance than the unmodified binder. But again, the effect of temperature is fairly significant. Like at 120 degrees, sections are failing in around 600 to 800 passes. whereas at 90 degrees, these curves were approaching asymptotic, which means it would take enormous number of passes to reach failure. So we stopped testing at around 5,000 passes here. Effect of rate of loading. Asphalt concrete is a viscoelastic material, so rate of loading has a big impact on how it performs. So what you see in this chart is asphalt concrete strain, and these are the strains at the bottom of the asphalt layer, and time of loading in seconds. So we started testing at NAPTF what we called slow rolling response tests, where we were testing at speeds of 0.25 feet per second. So it's basically very slow speed. And at that speed, you're basically measuring viscous flow of the material. So if you look at the stiffness behavior of asphalt concrete, at low temperatures or very high rate of loading, very high frequencies, you see almost elastic behavior. Then you run into viscoelastic behavior. And then at very high temperatures or very slow rate of loading, you see viscous flow. So when this is a log-log curve, so keep that in mind. So when you're in slow rolling response tests, you're measuring viscous flow. When you're measuring responses under falling weight deflectometer, you are measuring the elastic part of the curve. And this is where we were with the traffic test. So we still have very significant effect of rate of loading. And these are at different loads, 24, 30, and 36,000 pound wheel loads. And this chart here shows the effect of binder. So this is unmodified binder and polymer modified binder. And again, very significant difference in the performance. Cracking, fatigue cracking. Now, one of the advantages of full-scale testing, accelerated pavement testing, is you can see the evolution of distress in these pavement structures. And when you look at cracking, I related it to the asphalt strains. So we have transverse strain gauges and longitudinal strain gauges, and the two show very different behavior. What you see on the left side is a strain measurement from a longitudinal strain gauge, single axle, 3 axles, so you see 3 peaks and single peak. But one of the things to note here is that as the wheel approaches, you get your tensile strains, and most of those strains are recovered. So you do not have any significant amount of unrecovered strain or permanent strain. When you look at the transverse strain gauges, that's where you start seeing some strain accumulation. And this is for single axle and 3 axles. And what you see is as each of these axle approaches a strain, now you start seeing accumulation of strains. And it is this accumulation of transverse strain that results in the longitudinal crack in your pavement structure. So the first crack that you generally see is a longitudinal crack, and these cracks form right around tire edges. And why they form right around tire edges is something that will come later on in my presentation, where I'm going to use some of the work from Professor Alkari's research. And once these longitudinal cracks extend, they kind of become like asphalt beans, and then they start developing transverse cracks, and that's what results in your alligator cracking. And another thing is, whenever there is a crack formed, you want to know whether this crack is surface initiated or is coming from bottom, because most of the design procedures assume bottom-up cracking in the asphalt. In my 28 years at this facility, I have never seen a bottom-up crack. All the cracks have been top-down. And I remember a presentation given by Professor Andre Molinar from Delft University in one of the ISAP conferences, where the title of his presentation was Bottom-Up Cracking, a Myth. And I'm one of those people who have never seen. And we have built even thinner sections with 3-inch thick asphalt pavements, and still it's been top-down. So that was the asphalt material. How does aggregate material behave and subgrade soils behave? So what you're seeing in these charts is the measurements of deflection from multiple depth deflectometers. And one of the advantages of MDDs is you can look at deformation coming from each layer of the pavement structure. And what you see here is this is for medium strength subgrade. It's a clayey soil. So this is your total deflection. That shows kind of linear behavior. But when you start looking at the subgrade, it's showing stress softening. When you look at the aggregate materials, they're showing stress hardening behavior. So it's the combination of these two contradicting behaviors, stress hardening and stress softening, that results in almost linear behavior. What you see on the right side is for high strength subgrade, which was a sandy soil or a granular soil. The subgrade shows stress hardening behavior, and the aggregate layer shows stress hardening behavior. So the total behavior of the pavement structure is also the combination of that. So when you consider linear elastic behavior and you have materials that are showing stress softening and stress hardening, depending on where you are in terms of stress, you could be under-predicting or over-predicting pavement responses, which in turn results in under-predicting or over-prediction of pavement life. And that's what you can relate to what we observed under full-scale testing. So the measurements I showed in the previous slide was in an actual pavement structure. When you test these materials in laboratory, so granular materials are generally tested in a triaxial test, and you apply different combination of confining stresses and deviator stresses. So what I have shown here, these are the results for P209 crushed stone base material. And what you can see is the x-axis is the bulk stress theta and the resilient modulus on the y-axis. And you can clearly see as the stress magnitude increases, the stiffness of the material increases. So that's what we call a stress hardening behavior. On the right side is the chart for our sub-base material, which is P154. And in our studies, we used crushed screening. So it's a crushed material, and it also shows your stress hardening material. Whereas, if you remember in our design procedure, we are using an equation to compute modulus of aggregate layer as a function of subgrade CBR and the layer thickness, without giving any advantage to the quality of the material that we are using. Let's move on to the subgrade soils. What you see on the left-hand side are the results from low-strength subgrade, which is a silty clay. And what you see on the x-axis is the deviator stress and resilient modulus on the y-axis. So again, these are results from a triaxial test. And you can clearly see as your stress increases, the modulus decreases, and that's what we call stress softening behavior. And this is for medium strength subgrade. Again, as your stress is increasing, the modulus is reducing. These are from the lab tests. And we saw similar behavior through the MDD responses. So when we started traffic testing with the aircraft landing gear, how did these pavement layers behave? Does it relate to what we are seeing through lab tests and the MDD measurements? Remember these two sections, this is medium strength with conventional aggregate base, and this is low strength subgrade with conventional aggregate base. And I have shown here the pavement cross sections. So for low strength, you have 36 inches of sub-base and 8 inches of base layer. So you're looking at 44 inches of aggregate material that is stress hardening. What you see on the medium strength is 12 inches of sub-base and 8 inches of base layer. So you're looking at 20 inches of stress hardening material. So almost half the thickness compared to the low strength. And the results that I've shown here are permanent deformation as measured by multiple depth deflectometers for the different component layers of the pavement structure. On the low strength subgrade, what you see is the subgrade deflections are very low. It's the sub-base material that is accumulating permanent deformation. And this is the location at around 20,000 passes where we increase the wheel load from 45,000 pounds per wheel to 65,000 pounds per wheel, and that's when these deformations start increasing. It's a very different behavior in your medium strength subgrade test section. Your deformation in the subgrade is much higher compared to your base or subbase layer. This is your subbase layer. And something happens around 5,000 passes. As you can see, we see the change in the curve. And once we fail these sections, we generally cut trenches to look at the failure mechanism of what was happening. And what we saw was failure in the subbase layer with subgrade intrusion into the subbase. So, in pavement structures, when you have these different layers, there's a shear layer that sort of forms at each layer interface, and that's total deterioration of that shear layer, and now you have subbase failure occurring because of significant deformation in the subgrade, and now you have material flow. Why these curves turn upwards is the MDD was not located in the location of maximum rutting. It was not in the center, and it was on the side. So this material flow was pushing the tube of the MDD, and we saw that in the trenches. So to summarize the observations from accelerated pavement tests, HMA, or our asphalt concrete layer, shows viscoelastic behavior and significant effect of temperature and binder grade on pavement performance. For aggregate base and subbase performance, we see these materials show stress-dependent behavior, with aggregates showing stress hardening, and we saw failure in our subbase. We also had failure in base layer in some of the test sections. Our design procedures do not have any failure criteria for base and subbase materials. For subgrade soils, we observed stress softening behavior. Now, when you look at how are these materials accepted during construction, for aggregate materials, it's strictly gradation and the density is what is used for acceptance. No strength property is measured. And what are we using as an input property for a design? A modulus value. But that's something that we are not measuring. For subgrades, we are measuring CBR, which is not really an index property of the soil. And there are techniques available to measure modulus directly on top of the subgrade and aggregates, which could be used in a design procedure. So we saw how pavements behaved. We saw our design procedure. So where do we go from here so that we can bridge that gap between the predicted life and the actual life of the pavement structure? And that's something what I'm going to talk in this part of my presentation. So you can do advanced material characterization. There are a lot of lab tests that are available that characterize the viscoelastic, viscoplastic behavior of asphalt materials, the stress-dependent behavior of aggregate layers, and stress-softening behavior of subgrade soils. But you also need to have a pavement analysis tool that can use these input properties. And that's something we are currently doing. We are working on developing this program called PANDA AP, which is pavement analysis using nonlinear damage approach for airfield pavements, where asphalt layer is modeled as viscoelastic, viscoplastic, and the aggregate materials and the subgrade is modeled as nonlinear elastoplastic materials with evolving hardening. So for asphalt materials, we use kind of a combination of Shapery's model to look at nonlinear viscoelastic behavior, and Perzina type viscoplastic model to look at hardening and relaxation to account for permanent deformation in the asphalt material. For aggregate materials and subgrade soils, we are using nonlinear stress-dependent elastic model that incorporates the effect of stress level on deformation. And this work we are doing with Texas A&M University and Kansas University, and the models that are being developed are being verified with full-scale test results from NAPTF and NAPMARC. And There is no commercial software involved. It's a 3D finite element program. So once the program is ready, it'll be available for free download from our website for anyone. And currently, this program is going through critical evaluation, and we have around 20 subject matter experts in US and abroad that are working with the program to provide us comments. Because one of the things we also want is that program should be easy to use, because if it's not easy to use, people are not going to use it. So we are looking at the usability and the science behind the models, etc. We are looking at machine-based prediction models for airfield pavements. You know, we have been collecting the sensor data for last 30 years. So we think we have a significant amount of data that we can at least start looking at the new technologies that are available, artificial intelligence and machine learning. And we are working with the University of Illinois, and Professor Alkari is the PI on this project. And we looked at all the sensor responses and looked at performance models. The final reports are currently under editing process, so they should be out pretty soon for you to download. Here is a slide I took from one of my PhD advisors, Carl Monismith Lecture, that he gave in 2014. So he was working with Dr. Manuel Bejarano on a FAA-funded project when University of Illinois was Center of Excellence for Airport Pavement Research. And they came up with this chart where they looked at subgrade stress ratio and related it to strain with number of passes. And what they recommend is that if we keep subgrade stress ratio less than half, we can prevent subgrade rutting that could result in ultimate pavement failure. And in fact, you know, FAA worked or developed a new pavement evaluation process that replaces ACN, PCN. It's called ACR, PCR, Aircraft Classification Rating and Pavement Classification Rating. In the previous ACN, PCN methodology, there was an overload criteria of how many overload operations can you put on a pavement, but those numbers were picked up from thin air. There was no science behind it. So we have been doing research to develop an overload criteria for ACR, PCR methodology, and my colleague, Dr. Dan Offenbacher here, he has been analyzing the data to come up with the criteria. And subgrade stress ratio is what they found that best relates to provide guidance on overload. And I think this is something that we'll be looking for in the future to look at failure in the subgrade layers and also in the aggregate materials. Tests for performance prediction. You know, we are failing these pavements in accelerated pavement testing. Are there any lab tests that we can do on the materials that can relate to pavement performance? So we had recently completed 2 years ago test cycle 2, where we tested a lot of hot mix asphalt and warm mix asphalt with different additives for warm mix. And what we found is that when recovered asphalt binders do not meet minus 22 degree low temperature PG grade as required by the regional road temperature requirements, we observed cracking. Out of 6 sections that we tested, only 2 showed cracking, and these 2 had different warm mix additives. And the lab tests showed that. A delta TC lower than minus 2.5 degree centigrade also resulted in test lanes that showed cracking. When poker chip ductility was lower than 150%, cracking was observed. And asphalt binders that did not meet NCHRP 960 approach for 20-hour pressure aging vessel conditioning, surface-initiated cracking was observed. And again, all the cracks that we observed in NAPMARK in these warm mix asphalts were also top-down cracks or surface-initiated. We also performed tests on mixtures, and semicircular bending test that gives you flexibility index effectively distinguished between test lanes that exist in cracking and that did not. And the findings from this research are published in a TRB paper that is listed on the slide. And currently we have 2 projects going on under balanced mix design, which are part of Airport Asphalt Pavement Technology Program administered by NAPA. And the objective of these two projects is to come up with tests that relate to performance of these materials and pavements in the field. And they have verified some of this, and they're also coming up with newer tests which are more theoretically sound. Around 2006, 2007, we worked with the manufacturer of asphalt pavement analyzer to develop a APA equipment where we could apply 254 PSI. Because if you look at FAA 5370-10 advisory circular, we moved from Marshall mixed design to SuperPave, but there was no performance criteria listed. So we developed this APA, and Dr. John Rushing from ERDIC visited our facility, and he did significant amount of testing on his mixes as part of his PhD dissertation. And we developed a criteria that if a mix experiences less than 10 millimeters of rutting at 400 passes at 64 degrees, it is good enough to go on an airport and should not suffer significant rutting issues. And the rutting project under balanced mix design also showed that APA was the best performing test that ranked the materials according to their performance. So what they're doing is they're modifying this criteria for different temperatures and for different wheel loads. So you can have advanced material characterization, advanced models that use, but the most important factor that actually gets the least interest is the construction. If you don't build your pavement right, no matter how good your pavement was designed, it is not going to perform. So we have to come up with ways of characterizing our construction and the materials that are going in for acceptance. So we started this project for developing specification of use of non-nuclear technology in measuring properties of unbound pavement materials for both soils and aggregates, and develop a specification that could go into our advisory circular. And the equipment that we primarily looked at is lightweight deflectometer, which is much easy. You can carry it, you can do a lot more tests compared to a CBR, and it gives you a modulus value that you can use in your design. And by changing the drop of height, you can also capture the stress softening or stress hardening behavior of these materials in the field. And we worked with University of Texas at El Paso, and Dr. Sohail Nazarian was the principal investigator on this particular project. And there is a report. That report has not been published yet, but the results of the study are published in a paper that you can access. And the paper was published in the International Conference on Transportation Geotechniques. Once you know, as a designer, you design your pavement way in advance of construction. So you design your pavement, and you can look at the sensitivity of modulus to predicted pavement life. Once you go to your construction, you can develop your specification that what should be the range of my modulus for acceptance of this material so that it does not significantly affect my pavement life. And also, once you have built your pavements and you have the moduli value for each of these layers, you can put it back into your design procedure and see how your design life will be affected. Another thing to look at is the non-uniform contact pressure distribution under the tire. And this slide I took from Professor Al-Khari. And one of the things that you see here is they found that the edge ribs, the peak pressure is about 2.2 times the tire inflation pressure. And in the center ribs, it's about 10% higher than the inflation pressure. And to me, could be the reason why we see longitudinal cracks develop right along the tire edges. And this is something that happens every single time. And after I saw this work, we have started taking tire imprints under different tire pressures and wheel loads. And just by doing a simple math, assuming uniform pressure distribution in all these ribs, and taking out the unloaded area from these, the contact pressure is almost 16 to 20% higher than your tire inflation pressure. So to me, that's an important factor that we should be considering in our design procedure. And the plan is to develop something that can be incorporated into Panda. We are looking at other kind of instrumentation, like one of the distresses we see on airports once the tire pressure of the aircraft went high up was delamination in the asphalt layers at high-speed exits. So our French counterpart, DGAC, and their research group is called STAC. They have worked with Gustav Eiffel University to develop this device called ovalization device. And this device, you basically take out an asphalt core, install it right above the interface and once below the interface, and then you measure responses in the three principal directions. And we did some measurements at our test facility. Here is the ovalization device installed, and that's the HVS. We did tests at different speeds and different temperatures. And the results are published in a paper in the Journal of Road Materials and Pavement Design. Currently, we are evaluating the performance of cold central plant recycling materials. We completed construction of these sections last year in November as part of a Napa project. And these are just some photographs showing milling of the asphalt and then putting them in the plant to come up with CCPR material to be placed back. The sections are complete, and my technicians are actually heating the pavement, and probably tomorrow we'll be able to start full-scale testing on some of these sections, because currently we do not have any performance data available on cold central plant recycling. And to me, it's a great way of reusing our existing material, because the material that goes into airport pavements is of high quality. Why should we throw that material away if we can find a way of putting it back into our pavements? Causes savings in energy and costs. So the whole idea of our research is to generate performance data from full-scale tests, from instrumented airport sites, and from our lab, develop performance models for different materials and combine all this information to come up with airport pavement design procedures that can design pavements to handle aircraft traffic of today and tomorrow in a safe and efficient way. None of this work would have been possible without the support of a number of people. So I would like to acknowledge my management. I work for Airport Technology R&D branch, and our sponsor is the FAA Office of Airport Safety and Standards. I thank them for their trust in me for all the research project that I proposed, and they let me do that and come up with the findings that you saw today. All the support contractors over my 28 years career there. I started myself working for Galaxy Scientific. I worked for 9 years before I became a federal employee, and worked with some brilliant individuals from these companies, some of them with whom I'm still working with, and it's been an honor and privilege to work with them. Our federal organizations, ERDEC, we have done a lot of joint projects together. I know we have a big team from ERDEC, and we have had worked with almost each one of those individuals. And currently, they are actually evaluating our PANDA program. Federal Highway Administration, different airports and airport authorities, because without their support, we would not be able to go and instrument pavements. Because, even though we have 2 test facilities, we can change temperature and stuff, we are still testing under controlled conditions. And Scott Morrell, from when he was with Port Authority of New York and New Jersey, he gave us our first pavement instrumentation projects at John F. Kennedy, LaGuardia, Newark, and that's what gave us more confidence, and now we are working at different other airports. And then our industry organizations like NAPA, that is administering our Airport Asphalt Pavement Technology Program, and National Concrete Pavement Technology Center at Iowa State, that is administering Airport Concrete Pavement Technology Program. These two programs are doing research projects, and the idea is to come up with findings that can be taken to field in much quicker way. And then, of course, over these years, I have worked with different universities through research grants and agreements, and I've tried to list almost all the universities with whom I have worked with, and I'm still working with, whether it's material characterization, developing advanced material models, because even though the title of my presentation was Advanced Material Modeling, I am not a material modeler by any definition. What I do is pavement testing, material testing, look at the behavior, try to understand that, and then provide that information to the modelers to develop those advanced models and stuff. And I would like to end my presentation with this quote from Sir Arthur C. Clarke, which kinds of resonates with what Professor Al-Qadi mentioned about Professor Carl Monismith, that the only way of discovering the limits of possible is to venture a little way past them into the impossible. O.J. Porter in 1940 said that we should try to look for ways other than CBR that characterize the modulus of the materials, look at stress ratios and stuff. But for some reason, we really never went that way, because just building up on what existed was the easiest way. But I think this is what we should keep in mind, and I think the younger generation that is coming up is very capable, and I think they are very enthusiastic into moving into territories that we have not explored yet. Thank you for your attention.
Thank you so much, Nav. That was a fascinating lecture. I learned a lot about the history of the airfield and what's going on right now. So we're going to start with some questions. There's one here. We do have a microphone. Just raise your hand.
As far as I remember, there are two main failure criteria, namely rutting and fatigue cracking failure. I remember that there is an input for temperature in the interface of the program, software program. So is it possible to incorporate low temperature cracking failure to this approach?
So the question was that there are two kinds of failures that we talked about, rutting in the subgrade and fatigue failure in the asphalt layer. And is there any way of incorporating temperature? Low temperature cracking failure. So that is not addressed in a design procedure, but it will be addressed in the selection of materials. So currently you can't do that, but we are developing performance-related specifications, and the project that we are doing under balanced mix design for cracking will be accounting for that. And we are developing some new test procedures, and Professor Al-Qadi is the PI on that project and probably can provide more information. But it's coming. We don't have it now, but it's coming in the near future. Yes.
Other questions? I'm sure Scott is.
Anybody hear me?
Yeah, yeah.
Okay. So I'm a little torn because I got to be careful with this. So the FAA, right, they set national standards and they kind of put the guide rails on what you can do in the design of an airfield pavement, right? Right now you have materials where you have limitations, right? And I understand that point, but it seems like we're kind of constraining creativity a little bit with that. Like with these newer tools, it might allow for more innovation in design and optimization. But, and I mean, it's great what you're developing, and I don't even know you can answer this, but I'm a little concerned about that the policy will come down then, and we'll back to, well, you have to do this, this, and this, because we have to make it so that anybody can design a airfield pavement. And it really, I think this really highlights what a specialty it is. So I don't know, I'm sorry, Brad, I don't know if it's a question, but it's kind of a thought about it. It's really thought-provoking what you're doing, and it was a wonderful presentation.
Thank you, Scott. But it's a great question, you know. And I think you will start seeing developments in that direction. Our policy will still, I shouldn't say policy, a design procedure, the implementation will still be simple so that people without advanced knowledge can still do the design. But we'll try to put it in such a way so that advancement is all in the background. Like one of the things is that, okay, we're using Panda with these advanced models. What if someone doesn't have capability to get the material properties and stuff? So we are going to provide a library of properties. So if you don't have capability of doing the tests, if you can say that, okay, my mix has this polymer modified binder and my gradation fits this band, these are the recommended values to use in the procedure. And Panda will be available as an advanced analytical tool to do your sensitivity studies alongside far field. But I think you will be seeing more developments in far field also in the near future. Yeah.
So we've got time for one more question if somebody's got one.
Thank you for the great lecture, Nav. Kind of alluding to the last comment and sort of the end of your presentation, what do you think are some of the big like open areas for future advancements? You know, as you think of the younger generation that's coming on of like in 15 or 20 or 30 years, what do you think they should be working on? What do you think are the big open problems still?
Well, again, I think we are not solving all the problems with what we are working currently. As you said, you know, like non-linearity of the material. Of course, non-uniform tire pressure distribution are two of the big issues that they'll have to deal with. And also with new material technologies coming up every day, like CCPR and some other, and I'm pretty sure the speed at which material science is evolving, we will see a lot of additives that we will probably be able to use to make our local material suitable for airport pavements, but what are going to be the failure mechanisms of those materials? And then trying to develop failure models and incorporating in the design procedure. And all the data that we have been collecting over these years, how to use your artificial intelligence. Like, could we make our design procedure fully mechanistic in nature? I think that'll be the biggest challenge. And to develop performance models, you know, performance-based specifications is, I think, what is needed right now. Because currently, if a state or an airport has worked with some materials that performs well, but does not fit in our specification, they can't use it. But if we have performance-related specs, then if your material is meeting the performance, it goes into the pavement structure. And again, aircraft industry will keep coming up with innovations, you know, their wheel loads and tire pressures, because all they want to do is increase the range of the aircraft while keeping per passenger, per mile cost low, which means higher gross weights, higher wheel loads. because they don't want to reduce the wheel well volume because that would require putting more wheels, and increasing wheel well volume takes away their payload capacity. So I think some of these, and I'm pretty sure there are a lot more that I have missed. Yeah.
If that's okay, I will take one last question before we end the session. We got here.
Thank you, Navneet. It was the best lecture I've seen at this conference for sure, and probably in one or two conferences before.
Thank you.
Yeah. But
Scott, you're not my friend anymore.
but one of the things that, kind of getting on Scott's thing there was materials properties. Everything is designed based on our normal cement, ASTM 150. But the new specifications do allow other cements in there. And I've worked a little bit with the calcium sulfo aluminum cements, and they have very little shrinkage. And shrinkage is an important part. And I had some papers where I talked about you could get the joint specifications much wider and stuff. But the shrinkage is an important characteristics that's not being modeled right now. Is there any way that we can do research and do some modeling on shrinkage and how it affects the cracking for rigid pavements?
So I think that would be a project for ACPTP program. So you can submit your idea or suggestion to the panel there, and they'll probably look into it because we don't have capability of looking that at our facility. But I think this would be an ideal project for ACPTP.
Or Richard, he has an answer for that. No?
Here's the asphalt.
I was looking at him.
Well, Richard's answer would be if the cracking occurs, cover it with asphalt.
So with that, I just wanted to thank Nav again for an outstanding lecture. I think for Jesse, Nav was trying to tell you it's about time to use science in our pavement design. So it's if Banda gonna work or not, this is the first step, and we're gonna just keep moving it, so we are going in the right direction. And the same for the material characterizations that they are doing at NABA. Nav, that was an amazing lecture. Thank you so much again for being our Carl Monismith Distinguished Lecturer today. Thank you so much.
Thank you.
So, thanks everybody for coming. In the Geo-Institute, we actually have a really strong tradition of these named lectures. We have 5. We have the Monismith Lecture that's traditionally given here at the Pavements or the ICTD conference, and then we've got Terzaghi, Seed, Peck, and Prakash. You can watch all of these on our YouTube channel. The NAV is the 15th Monismith Lecture, and I think we've got 13 of the 15 up on the YouTube channel, so you can go watch those. For those who watched the live stream today, thanks for joining us, and same thing for you guys. You can go watch all those other lectures. The other thing they should watch, I do a show every week called Director's Cut where I interviewed GI members. Nav was the guest last week. So go check that out. Get to know him a little better. It was fun, right?
Yeah.
I mean, you have to say it because you're up here on stage. Yeah, it was the summer farewell one, so we looked good. We were stylish. So thanks everybody again for coming today. We really appreciate it. And we should get as loud as we can for Nav. Congratulations. This was really great. Next thing up, everybody, we're going to close out the exhibit hall with a reception right now, but it's also the poster reception. So we're going to have food and bars up on the 4th floor as well where those posters are. So go check it out, support our poster presenters, support our exhibitors and sponsors, get a drink, get a bite, and have a good time. Thanks for coming.
Thank you all. Thank you.